Hi, we start the new section, this 4J, the geometric progression. So in the previous sections, so we talked about the annuity with whose payment amount is increasing linearly, but here the increasing geometrically. So think about the so let I be the annual effective interest and consider the time diagram. So time diagram start with 0 and end with n. And the payment amount is 1 plus k at time 1. And the square of 1 plus k at time 2. And the cube of 1 plus k at time 3, and so on. Then at last, 1 plus k to the nth power. We want to make a formula for present value, and the present value is actually just a right angle n at interest rate j, and here the j is not annual effective interest rate, but the j is equal to I minus k over 1 plus k. So I is the interest rate, and the amount is increasing. The payment amount increases by a factor of 1 plus k. So the interest rate I basically makes a discount of the payment when we evaluate it at present. But we basically subtract k because the payment amount grows at the rate of k. So basically the difference of the I and the k is the more important quantity. Then we divide by 1 plus k. So this is slightly smaller than I if I and k are positive. So this is the present value formula. And the proof is not super complicated, but we need just one idea. So think about the present value of the first payment, 1 plus k. So it goes back 1 year to evaluate at present. So this is actually equal to 1 plus k times v. The v is 1 over 1 plus I. So this is actually the 1 plus k over 1 plus I. Okay, so let this number as the v tilde. Because the v is defined as 1 over 1 plus k, but here the 1 is replaced by 1 plus k. So just slightly different quantity. So just we name this as v tilde. Then what is the present value of the second payment? Second payment amount is 1 plus k square, the square of 1 plus k. So this present value of this amount is 1 plus k to the power 2. So square of 1 plus k times the v square, because we go back 2 years. So we have to multiply v square. We have to discount by the v square. And the v is, again, the 1 plus I. So we can say that this is 1 plus k over 1 plus I, entire quantity square. So we can write this as the v tilde square. And you can imagine how this continues. If we evaluate the third one, this becomes the v cube, the v tilde cube, and so on. So that means the present value is the total of these n payments. So this is equal to the v tilde plus the v tilde square plus up to v tilde n. So we can write this as an right angle j if we define if J is defined as B tilde is equal to 1 over 1 plus J. So J, if the J corresponds to B tilde, then we can write this as AN right angle J. Because in general, the AN right angle I is equal to V plus the V square plus up to the V to the nth power. So remember that the first $1 at time 1 is worth V at time 0. $1 at time 2 is worth V square at time 0, and so on. So AN right angle I is the V plus V square plus V cube plus up to the V to the nth power. So PV, so this PV is also expressed as A right angle NJ if the 1 over 1 plus J is the B tilde. Or if we express this as a formula for J, the J is equal to 1 over V tilde minus 1. So you can multiply 1 plus J on both sides of this equality. Then that is the V tilde times 1 plus J is equal to 1. So then that we move the term V tilde, then we divide by V tilde, then J is equal to 1 over V tilde minus 1. And the 1 over V tilde minus 1 is this one. So V tilde is defined as this quantity, 1 plus K over 1 plus I. So that means the J is equal to the reciprocal of this quantity. So 1 over I over 1 plus I over 1 plus K minus 1. So 1 is 1 plus K over 1 plus K. So you can say this as I minus K over 1 plus K. So this is the J. So this coincides with this claim. So now that we have the theorem, so the present value of this, the geometric cash flow is represented by A right angle NJ. And here J is I minus K over 1 plus K. And the K is percentage change of the payment amount and I is interest rate.